our problem, a random variable follows a uniform distribution on the closed interval AB. That means its probability density function is equal to 1 over b minus a when t is in the closed interval from a to b, and 0 otherwise. Because this is a probability density function, okay, that means the area under the function is going to be equal to 1. Now, we want to find all moments about the mean for this distribution, and we want to verify using the moment generating function. So, for our first step, we'll write down the definition for the moments about the mean, and then we'll find the mean. So to start off, once we found the mean, then the kth moment about the mean is given as the expectation of random variable minus the mean raised to the kth power. So in our case, we're going to take an integral of x minus the mean raised to the kth power times our probability density function. For the mean, okay, we need to find that first. So it's going to be the expectation of our random variable. That's going to be given as the definite integral from a to b of x dx over b minus a. So for an antiderivative of x dx, we just use 1/2 x squared. We evaluated b and a, take the difference, using the first fundamental theorem of calculus. That's going to give us 1/2 b squared minus a squared over b minus a. The numerator is a difference of two squares, so b plus a times b minus a. B minus a's go away. I'm left with 1/2 a plus b. Our check, the picture here, this is just saying that the mean occurs at the midpoint of the interval. So that's something we definitely believe. Let's compute the moments about the mean. So we want to compute definite integral from a to b, x minus mu to the kth power, dx over b minus a. Here I'm going to leave the mean as mu until we get to the end, and then we'll substitute in a plus b over 2. So for now, this is just some constant. To solve this, we're going to do a u substitution, then we'll invoke the first fundamental theorem of calculus. So we'll get 1 over k plus 1 times 1 over b minus a times x minus mu to the k plus 1. We evaluated b and a, take the difference. That gives this expression, and this cleans up nicely. So we want to work out b minus mu and a minus mu. Okay, we note we'll have b minus a over 2. Then for a minus mu, we're just going to have the negative of that. Now, that gives this expression. We'll note when k is odd, this becomes a 1, and then we're taking the difference of two items that are equal. So we get 0. If k is even, then we're just going to take the sum of these, so we'll have twice. That 2 is going to go here to give us a b minus a over 2 flipped over. So I'll cancel one of these to give us 1 over k plus 1, b minus a over 2 to the kth power. Now, let's check this against the first 4 moments of interest. Okay, we have the mean. Second moment about the mean, it's going to be the variance. So we have 1/12 b minus a squared. Okay, note here, if we have a wide interval, then the variance is going to increase, and that agrees with what we think of variance. So that's going to be the spread. For the third moment, we're going to get 0. So that's going to mean that the skewness is 0. And again, that makes sense because our distribution is uniform, it's flat, it doesn't tend to one side or the other. So that would mean skewness 0. Finally, for the fourth moment, can we work that out? Then we use this to define the kurtosis. So the kurtosis is the peakedness. So the peakedness is basically a measure against a normal distribution. And we note here, okay, what happens? We get a 9 over 5. So this is going to mean that our distribution is platykurtic. Platykurtic means we have long, thin tails. Now, for a uniform distribution, we don't have any tails. So we're going to be defined on some region, and then it chops off, everything goes to 0. So platykurtic. Now, let's compare with the moment generating function. So this will be defined as, okay, we're going to pick a real number t. We'll take the integral over the real line of e to the tx f of x, okay, the probability density function. This integral is with respect to x, so we treat this t as a constant. Now, when this integral is defined, okay, that'll be when our moment generating function is defined. We make sense of this by noting e to the tx. We can expand this out as a power series. And if we take this integral term by term, then the kth raw moment for our distribution is just going to be the coefficient of t to the k over k factorial. Now, if we work this out and get some function with a nice closed form, the way I extract those moments, so for the kth moment, I'll take k derivatives and then evaluate at t equals 0. So this business of taking the derivatives is going to get rid of the k factorial. Now, for the uniform distribution, okay, we set up our definition. So we're taking definite integral from a to b of e to the tx, dx over b minus a. Here, I want to integrate that e to the tx with respect to x. So just remember, we're treating t as a constant. Okay, it's going to be some number that we set over here. So for the u substitution, we'll have u equals tx, du equals t dx, and then we just proceed. So first fundamental theorem of calculus gives us, you'll have 1 over b minus a, e to the tx over t. We evaluate the x at b and a and take the difference. So here we have our moment generating function for the uniform distribution. Now, to extract moments, we have two options. One, I can apply the quotient rule and then use L'Hopital's rule to evaluate. Or, okay, much easier, will be just to take the e to the bt, e to the at, do series expansions, and then see what comes out. Now, if we're going to do the series expansions, okay, I'll have 1 over t b minus a. Then for e to the bt, we have 1 plus bt plus b squared t squared over 2 factorial and so on. And likewise for e to the at. When I take the difference, okay, we simplify everything. I'll have 1 plus t over 2 factorial, b squared minus a squared over b minus a. And as we work out, we'll see the general term is t to the k over k plus 1 factorial times b to the k plus 1 minus a to the k plus 1 divided by b minus a. So we just need to make sense of these terms here. For the kth raw moment, we extract the coefficient of t to the k over k factorial. So this will leave this quotient. We'll have 1 over k plus 1 in the front, okay, to match up to k plus 1 factorial. Now, to get the kth moment about the mean, that's going to be the same as the kth raw moment of x minus the mean. So what we want to do is, I want to replace a with a minus mu, b with b minus mu. We've done this calculation before. Then, if we substitute into this expression, what comes out is familiar. And we get the answer that we had before. So our work checks out.